Hi, welcome to this lesson on calculus. What is differential calculus? So first of all, let's have a look at an introduction to calculus. So many mathematicians over many years developed this field of mathematics known as calculus. In short, calculus can be divided into two main areas of study. So what are these areas? Well, we have differential calculus and integral calculus. So differential calculus deals with the rates of change of different objects in relation to each other. So this is useful in many real-world applications. So we tend to model a lot of real-world applications with functions, and functions will change over time. So as time goes on, the way your function might change rapidly. It might increase, decrease, increase again. Like for example, the stock market's going up and down. We want to know what is the behavior of these changes over time and how fast do they grow? How fast do they decrease? Then integral calculus is the inverse of differential calculus, and these can help us find the equations that we need in order to model the real world around us based on the properties that we can see from functions. Okay, so we will be focusing on developing the tools to study differential calculus. So the core concepts that we are going to be studying are cubic polynomials, the concept of what we call a mathematical limit, the derivative of a function, which makes up the key bulk of calculus or differential calculus, the derivative laws for certain algebraic expressions, finding equations of tangents to points on various functions, properties of the second derivative of functions, as well as looking at the first derivative as well, how to sketch cubic functions, which is really important, and then how to solve optimization problems using differential calculus. Well, why do I need to study calculus? Well, over the course of history, mathematicians have tried to describe the world that we live in. And the way we try to do that is to use functions. So we've seen a few functions in our study so far. Functions such as the straight line linear functions, so of the form y equals mx plus c, where m is your gradient, c is your y-intercept. We've looked at parabolic or quadratic functions, so functions of the form y equals ax squared plus bx plus c. So these are the either happy face or sad face parabolas. We have exponential functions that we looked at. So we saw that functions grow exponentially, so they grow very fast or they decay exponentially. So classic examples are a virus generally grows exponentially in the wild. And in chemistry, we have certain things like protons, neutrons, and all those chemicals and atoms and stuff that can decay over time. Okay, and then hyperbolic functions we've also had a look at. So those are functions that would look something like this, the rectangular hyperbolic functions. So the reason we usually study linear functions first is because it's easier to see what a gradient of a function at a point is. So recall, as we've said, that a linear function of the form f of x equals mx plus c has a gradient value of m at any given point on the straight line. So what does this mean? It means that the gradient is constant. It's this constant number m. So the function, we say, grows at a constant rate. Okay, what is the importance of the gradient of a function? Okay, so the gradient tells us how fast the function is changing at each point. And this in turn tells us which direction as well the function is going. So whether it's increasing or decreasing as we go along the x-axis from left to right. So this is useful information because we can interpret the speed and the direction of a given function at any point in time. And that has a direct impact on the given function. So for example, if you consider the function f of t, where t is the independence variable and f of t is the outcome, your y, your dependence variable, it's 3 times 2 to the power t minus 1. So this is an exponential function, right? Because the exponent, the variable's in the exponent. So this function could potentially model the growth rate of a certain virus at any given time t. So if we wanted to get a sense of how fast that virus is growing at any given point in time, and if the virus will ever slow down, we can analyze the gradients at each point of the function and then note the trend of the gradients. Okay, but how exactly can we work out the gradients at an exact point on a function? I mean, for a linear function, it's quite simple, right? Because we can visualize the gradients of the line as the rates of change of the y values over the x values. So that's the gradient formula in general for the straight line. However, if you're looking at nonlinear functions such as the exponential function we looked at earlier, f of t equals 3 times 2 to the power t minus 1, well, that's not linear. However, we can approximate what we call the average gradients between 2 points on a function, and that is using a straight line. So that's why we study straight lines, first of all, because the gradients is very obvious to us. It's the change in y over the change in x. That's how fast that straight line grows. It grows at a constant gradient of m, which is the change in y over the change in x. So this is where the power of differential calculus can help us now. So that's the whole reason why we study differential calculus. We can actually pinpoint the exact rate of change. The exact rate of change, which is the gradient at an exact point on any function. That's key here. On any function using what we call the derivative of the function at that exact point. So, differential calculus can be extremely powerful when we want to analyze the behavior of a function. So when we study functions, we are mainly interested in the following properties of these functions. What's the domain and range of the function? What are the x and y intercepts, if there are any? Are there any asymptotes? So recall asymptotes are these either vertical or horizontal lines. Could actually be any straight line, but generally it's vertical or horizontal lines where your function can approach that line, but then never quite reach it there. Okay, when is the function increasing or decreasing? That's really important. Does the function have any turning points? What is the general shape of the function? So differential calculus will give us all the necessary tools to answer all of these questions. And that is why it's so useful to understand differential calculus, as it'll allow us to sketch various functions and then describe the behavior of those functions. So just as we said with the example of the stock market, graph could look like that. Okay, so it could be increasing over time, then reaches a turning point and then comes down again, and then reaches another turning point, then goes up again, increases, hits a turning point, then comes down again. And this all changes over time. And that could be the stock market price of a certain commodity, for example. Okay, so analyzing the behavior of functions, how they grow, how they increase, how they decrease, where they turn, all these important concepts are studied through the field of differential calculus. All right, so that's an introduction to calculus. I'll see you in the next one.